Hello again. Welcome to the third module of the webinar on nanoscale phase change memory devices. In this module, we're going to discuss about the fundamentals of the phase change memory or PCM nano devices. We have already learned that PCM is an emerging computer memory technology. PCM is fast, dense, and non-volatile. And we already learned from our previous module that the meaning of non-volatility for the memory is that the information stored in the memory will be retained even when the power is turned off. Now, there are various cell designs reported for this memory device, and the most common feature is that there is a phase change material placed between two electrodes. The cell design that you see here is known as a mushroom cell. And in this case, the phase change material is shown as the blue colored region. And here, the blue colored region has one type of state and the red color region has the other type of state. Now here, the two electrodes are arranged in the vertical position. That's why one is known as the top electrode, another is known as the bottom electrode. In many of the cell designs, we have such top and bottom electrodes, but in some lateral cells, the two electrodes are arranged in the lateral fashion. Now, in these cells, we always would have some phase change material, as you see, as the light blue color. The most common phase change material is the germanium antimony telluride, which is also known as the GST, and the common composition for that is the 2,2,5 composition. The resistance of the phase change material can be switched between the different resistance levels when appropriate electrical pulses are applied. The high resistance state is called the amorphous or HRS, and the low resistance state is called the crystalline or LRS. To switch from the low to high resistance state or to amorphize this cell, we need to apply a very high amplitude electric pulse, which is also known as the reset pulse. The reset pulse would have such an amplitude so that a small portion of the material is melted. So the temperature at this portion of the material has to exceed the melting temperature of the GST material. And then we also end this pulse with a very sharp fall time. During this sharp fall time, the molten material is cooled down or quenched abruptly. So this leaves a disordered state in this smaller active region of this material, and that disordered state is known as the amorphous phase. And because of the disorder of that state, we have the HRS in this material. Here we can see the schematic representation of the disordered amorphous state. Here the different colored circles represent the different atoms included in the germanium antimony telluride material. Now, when we want to go from the high resistance state to the low resistance state, or when we want to set the cell, we apply a set pulse. And in this set electrical pulse, we have a lower amplitude as compared to the reset pulse. Also, in the set pulse, we have a longer fall time. And during this fall time, the disordered atoms in the amorphous state get enough time to get into its ordered structure in the crystalline structure. Now, in the crystalline state, we have low resistance because of this ordered crystalline lattice. Now, one thing to notice here is that during the set pulse, the phase change material does not have to melt, but the material temperature should exceed a level temperature that is known as the crystallization temperature. Now, at any state, when we want to read a cell, we apply a low voltage read pulse or a low voltage DC sweep. We apply low voltage so that there is no disturb in any state of the cell, so that we do not program further during the reading of the cells. Now, depending on the size of the cell, The high resistance state can be in the order of 10 to the power 7 to 8 ohm, which is like 10 mega ohm to 100 mega ohm. And the low resistance state can be in the order of 10 to the power 2 to 3 ohm, which is in the order of kilo ohm or less than that. Now, the LRS also has two states. One is known as the hexagonal closed packed, which is obtained by annealing the cell for a few minutes at the 400 degrees Celsius. This HCP state is not obtained by electrical pulsing. Only by annealing at this temperature or by heating at this temperature we can obtain this state. The other state at the LRS is known as FCC, which has slightly higher resistance than the HCP state. At the FCC phase, we can obtain the FCC phase by annealing at the 180 degrees Celsius. This FCC phase can also be obtained with the means of electrical pulsing. Now, because of this very large memory window between the high resistance state and the low resistance state, the PCM, HRS and LRS can not only be easily distinguished from each other, but also we can accommodate various other program states in between the HRS and LRS. These intermediate states can have resistance levels that are in between the LRS and HRS levels, and these intermediate states are also known as the mixed states. In these mixed states, we have the cells in various proportions of the amorphous and crystalline states. Now, these different phases in this cell can be located differently, so we also observe significant variability in these mixed states. Now, when we program PCM cells into many cells like this with some intermediate states, we call such operation as the multi-level cell or MLC operation. In the MLC operation, we have more than 2 levels. So, say for example, if we have 4 levels of operation, these 4 levels should have distinguishable resistances corresponding to each of their states. And when we have 4 levels of memory operation, we also call it as a 2-bit memory operation. In our last module, which is module 4, we're going to learn a lot more about the MLC cell operation and the other reliability factors related to the PCM cell operations. But before we conclude the current module, we're going to learn about how to fabricate and how to characterize the PCM cells. So here we are showing an example of the germanium antimony telluride 225 line cells. And here you can see the SCM image or the scanning electron microscope image of these line cells. Here you see that these cells look like the dog bone shape, and the GST material lies in the middle of 2 laterally placed electrodes. So here the right side of the electrode is here and the left electrode is here. So instead of the top and bottom electrode, in the lateral arrangement we have the left and right electrodes. And in the middle we have the GST material. So you see this dog bone shape because the middle width of this cell is the active region in this cell, and this is extremely thin. So when we want to make this cell extremely thin, we have to go toward this dog bone shape. But we can also get a rectangular shape, but that rectangular shape would not have such extreme small width in the middle. Now the process steps would include a lot of the setups. For example, we have to grow the oxide first, and we have to open the trench, then we have to deposit the metal, which you see here as the blue. We have to polish the metal, and then as the red we are representing the GST film deposition. Then we pattern the GST film, and finally we cap the top part with silicon nitride. So the line cells that you see here are 50 nanometer thick, and they are on silicon dioxide. They have bottom metal contacts and they are capped by silicon nitride. Now you may wonder whether these are nano devices or not. The answer would be yes, they are nano devices. Why? You may wonder that their length is over 100 nanometer, and by definition any device is called nano device if their dimension is below 100 nanometer. So the answer why this is nano device is that we call a device nano device when the device has a sub 100 nanometer dimension in any of its dimension, either length or width or thickness. So these devices are already 50 nanometer thick, which is already in the nanoscale regime. That's why these are already nano devices. So no matter what width and length we take for these devices, all of them would be nano devices because of the nanoscale thickness. These devices are fabricated in the clean room facilities where there are certain standards for cleanliness, and the users also have to wear the gowns for the clean room. These devices can be imaged with the electron microscope. Because these are in the nanoscale range, we cannot see them under the optical microscope. So one way to see them is under the scanning electron microscope image, and this is how a SEM imaging tool looks like. And this is an example of the SEM image. But sometimes we want to know further about the cell. For example, in the SEM image, we cannot really tell the difference between different materials or different states. So we often do advanced imaging, which is also another type of electron microscope imaging. And this is known as the transmission electron microscope or TEM image. Under the SEM image, we cannot distinguish the different phases of the GST material. But when we go to the TEM imaging, we can distinguish different materials and different phases of the GST material. Now this is how the electrical characterization setup looks like. This is a specialized characterization setup which is known as the cryogenic probe station. In this station, there is a chamber where we can go up to various temperature and pressure ranges, and we can take a look at the measured region with the help of an optical microscope and a monitor. And this is how a room temperature probe station looks like. Here also we have optical microscope, several lenses, and we also have monitor to look at the area. But in this case, we do not enclose, or we do not really change the temperature. Rather, all the measurements are done at the atmospheric pressure and the room temperature. Now, when we want to apply programming pulses to these devices, either we can apply a single pulse or we can apply pulse trends. Pulse trends are often applied to go to the intermediate states more precisely. And we're going to discuss about more details about those MLC operation in our next module. So thank you very much for your attention on this module.